second type of redox reaction is called a decomposition reaction. So this word comes from decompose. This is the opposite of synthesis. So remember, in a synthesis reaction, you are making one product. In a decomposition reaction, you have a single reactant that breaks down into multiple elements, or breaks down into whatever formed it. So this is the opposite of synthesis. A single reactant breaks into multiple elements or new compounds. This often requires an energy source. So if I flip back to this example that we did here, letter F, NH4NO3. Notice this is the first, this is the only reactant, and it's just breaking down into multiple things. We would not call this a redox reaction because there's not a single element anywhere in here, but it is still decomposing. It is still breaking down. So anything that has a single reactant breaking down into multiple products is considered decomposition. So this is like if I had compound AB breaking down into elements A, which this one's going to be diatomic now, so I'll put a little 2 on it, plus B. Again, we'll do our demos on a different day, that way you can see. But if I have H2O2, this is hydrogen peroxide. Do y'all know what hydrogen peroxide is? You've heard of it? So hydrogen peroxide, usually you have it like in your medicine cabinet where you keep like rubbing alcohol, something to like sterilize, clean a wound, something like that. We keep it in brown bottles because that helps it to decompose slower. If it has a clear bottle, it will decompose more quickly, which just turns it into water and oxygen gas. For this reason, you should replace your hydrogen peroxide. You should replace your hydrogen peroxide anytime that it gets expired, because likely what you have left is just decomposed hydrogen peroxide, or at least partially or even mostly decomposed hydrogen peroxide, which is just going to be a container of water. So if it's like old and you haven't replaced it in a long time, they cost like $1 at HEB or Walgreens or whatever, but replace them, because the oxygen gas will escape as soon as you open the container and you break that seal. The oxygen gas will leave, and the rest of it breaks down into water, so if you pour water on your cut, it's not going to sterilize it the way that hydrogen peroxide would. Y'all know what I'm talking about, right? Okay. So H2O2 breaking down into water and oxygen gas. If we're balancing our equation, and this one is starting with words, or I have a combination of formulas and words, I'm going to write out H2O2, I'll give myself space here, decomposes into H2O, which is my formula for water, plus oxygen gas. But oxygen is O2 because it's diatomic. It's one of my Brinkelhoff elements. So the fact that I have O2, my single element here, the fact that I have that as part of this reaction tells me how will I classify it. What type of reaction is this? The color might be a hint too. Redox. Okay, so single element anywhere in the equation tells you it's going to be a redox reaction. And then the fact that I have a single reactant breaking down into multiple products, single reactant tells me what? Single reactant is what type of reaction? Decomposition. Perfect. Good. Decomposition, like decomposing. So that's what's happening. H2O2 will break down into water and oxygen gas. Let's balance this equation. So if I have my arrow that I drew for myself, hydrogen and oxygen, I have 2 hydrogens, 2 oxygens on my reactant side. On my product side, I have 2 hydrogens, and 1, 2, 3 oxygens. Since I have oxygen in multiple locations, you have to use a little bit of critical thinking with this one, where we run into the same thing. This side of the equation is always going to have an even number of oxygens because it's O2. So no matter what coefficient goes here, it's going to be even. On this side, anything I put in front of here is going to also make something even, but this 1 is going to make it odd. So if I need this to end up equaling this, this side is going to have to end up being even at some point. So I'm going to change H2O. I'll put a coefficient of 2 here. So 2 times 2 hydrogens gives me 4 hydrogens. 2 times 1 oxygen gives me 2 oxygens, plus the 2 oxygens from O2. So I have a total of 4 oxygen atoms on my product side. On my reactant side, if I put a coefficient of 2 in front of H2O2, my only reactant, 2 times 2 hydrogens gives me 4, and 2 times 2 oxygens also gives me 4. So it's straightforward to balance it as long as you understand what you're looking for. This all comes with practice. Alright, last example, and then we will pack up, is mercury 2 oxide decomposes when heated. So you will get examples like this in your practice and on your tests, quizzes, anything that we're assessing you on, so you still need to know your nomenclature from our previous unit. Mercury 2 oxide, if you were writing the formula for that, you have mercury, which is Hg. Mercury is one of our transition metals right here. So looking at our periodic table, we don't know the oxidation number for it, but the name tells you the oxidation number is 2. So this is going to be a plus 2. And oxide comes from oxygen, which has an oxidation number of what? Negative 2. So O with a negative 2 charge. That crisscrosses, becomes Hg2O2. But you don't keep it as Hg2O2. You reduce it down, just like we did with Mg2O2. You're going to reduce that to just HgO. So HgO decomposes when heated. So if it decomposes, that tells me it's a decomposition reaction. If this is going to break down, there is only one possible way for it to break down. It's going to produce what and what? Perfect. Mercury, which is Hg, plus oxygen, which is not just O, but O2 because it is diatomic. Why don't I put a 2 on Hg? Perfect. So underneath this, when I balance it, I would list Hg, O, I have 1 and 1, and then I have 1 and 2. My mercuries are balanced, my oxygens are not. So I'd put a coefficient of 2 in front of HgO. Now that brings me to 2 and 2. And then I need a coefficient of what where? 2 in front of Hg. Perfect. And that gives me 2 of those. Last thing we're going to do is classify this based on what we have. So if I have a single element anywhere in this, this is a single element, this is a single element, this is a decomposition reaction. Oops, sorry. I did that wrong. Y'all are making me nervous because you're packing up early. Stop packing up. Because we have single elements, it's not decomposition. What is it? Single element, single element. I even used the wrong color. So single elements means what? Perfect. Redox reaction, but it is decomposition. That's just not why we can tell it's decomposition. This is why we can tell it's decomposition. So we can tell it's decomposition because of its single reactant breaking down into multiple products. Redox because of the single elements.